Welcome friends. So we are discussing transient response of series RL circuit, RC circuit and RLC circuit. In this module we have understood the fundamental properties of inductor and capacitor and how they perform under transient state and steady state. We shall discuss briefly few numerical problem to understand these concepts. So let us say, consider this figure 8. We have a network. So switch is, please follow the language, the switch is moved from position 1 to 2. That means switch is initially at position 1, then it is moved from position 1 to 2. That is why the arrow symbol is given in this direction, right? So it is moved from position 1 to 2 at t is equal to 0. So switching instant is t is equal to 0. We should evaluate I, di dt and d2i dt2 at t is equal to 0 plus. So let us try to understand or analyze this circuit. When the switch is placed at position 1, so then the circuit roughly looks like this. It's simply this circuit: 10 volt source, 100k resistance, 0.1 Henry inductance, and this capacitance, which is equal to 100 nano. It is kept isolated from this circuit. So when this circuit is placed at or switch is placed at position 1 for a long time, that means this circuit reaches at steady state. That means that circuit reaches at steady state, and immediately we can draw conclusion from here that inductor will behave as short circuit. In the steady state condition, inductor will behave like a short circuit. So when the switch is reached at steady state, then due to the short circuit, inductor will offer zero resistance or zero reactance. Okay, so this is effectively directly represented by a short circuit like this. So I0 minus will be nothing but 10 by 100k, which is equal to 100 microampere. I0 minus, that will be 100 microampere. So from this result we can directly say that current flowing through the inductor does not change instantaneously. So I0 minus is equal to I0 plus, that will be 100 microampere. So this is your first answer. So current at t is equal to 0 plus, that will be 100 microampere. So just before the switching, current was 10 by 100k, which is 100 microampere. So when the switch is placed from 1 to 2, even though the 10 volt source is not connected at that time, but this inductance has the property of not allowed to change its current instantaneously. That is why it will hold that 100 microampere current for a moment. So due to this fact, I0 minus, that will be equal to I0 plus. So it remains as 100 microampere at t is equal to 0 plus. So we have first answer with us. Now write down the second equation or KVL equation. What is that? When the switch is placed at position 2, then this should be your KVL equation. This should be your KVL equation. What is that? First of all, the resistance drop, which is 100 into IT plus inductance drop. What is that? 0.1 into di dt. So this term. And what is the voltage drop across capacitance? It is 1 by C integration IT dt. that will be is equal to 0. Now 1 by C means 100 nanofarad. So 100 nanofarad means it will be 10 to the power 9 goes in the numerator. Okay, so if you substitute at t is equal to 0, okay, now let us follow what is written here. Since at t is equal to 0 minus, that means we refer as position 1, capacitor is not charged. That is true because capacitor is isolated. So capacitor is not charged, so it is not possible to build any voltage across that capacitor. So we can directly write this equation: Vc 0 minus Vc 0 plus, that will be is equal to 0. Okay, so this thing is instantly becomes 0 at t is equal to 0 plus. This is true for t is equal to 0 plus. So I repeat again why this is 0, because you see initially when switch is at position 1, then that capacitor is kept isolated, so no current flowing through that capacitor. That is why it is not possible to build any voltage across that capacitor. So that is why we can write Vc 0 minus, that is equal to 0. So just after the capacitor, now when the switch is now at this position, capacitor does not allow to change its voltage instantaneously. So just after the switching, that will also become 0. So we can write this equation, or we can just neglect this term, the capacitance voltage, by making it 0, and it is true for t is equal to 0 plus only. Okay, so we can write this equation into I 0 plus 0.1 into dit dt t is equal to 0 plus, that will be is equal to 0. So now I 0 plus is how much? I 0 plus is 100 microampere. So if you substitute and if you solve this equation, you will get dit dt at t is equal to 0 plus, that will be is equal to minus 0.001 ampere per second. That is very important. You should mention the unit. It should be ampere per second because it is di dt. So we have solved the second term as well, di dt. Now let us solve for d2i dt2, right? So we take from the equation 1, that means this equation, 100 di dt plus 0.1, sorry, it should be 100 I plus 0.1 di dt plus 10 to the power 9 by 100 integration 0 to t I dt is equal to 0. So now if you take derivative of this equation, though this will become 100 di dt plus 0.1 d2i dt2 plus this term will become 10 to the power 7 it, that will become 0. So from this expression, it is exactly written in here, 100 into di dt plus 0.1 into d2i dt2 plus 10 to the power 7 into it is equal to 0. Now if you know the di dt at t is equal to 0 plus, it at t is equal to 0 plus, so you should evaluate d2i dt2 at t is equal to 0 plus. So if you solve this, you will get d2i dt2 that will be equal to minus 9990 ampere per second square. So in this way we can solve the d2i dt2 for this network at t is equal to 0 plus. With this, I am ending here. Let us discuss few more examples on the next session. Thank you.